This meeting is being recorded.
Today we are going to see a famous example of an uncountable set of measure 0. This set is called Cantor Set. And first we start with the construction of Cantor Set. How do we construct Cantor Set? Consider the unit interval, closed interval 0, 1. We call it C 0. And there is only one interval in this set. C 0 contains only one interval. And we divide this interval into 3 equal parts and remove the middle portion. So it will be closed interval 0, 1 by 3 and closed 2 by 3, 1. So we get two closed intervals. And this we call the union of these two sets as C1. And for constructing C2, what we do is we take both the intervals in C1, divide these intervals into 3 equal parts and remove the middle portion. And we keep on doing this thing. And then we get C3, C4, etc. And then we take the intersection of all these sets. And this set is the Cantor set. And if from the construction we can say that C0 contains only one interval, C1 contains 2 intervals, C2 contains 4 intervals. Every time we divide an interval into 3 and remove 1. So every interval gives 2 new disjoint closed intervals. And every time, so when we constructed C1 from C0, we got interval of length 1 by 3. Each subinterval is of length 1 by 3. When we divide these intervals into one third, we get intervals of length 1 by 9 or 1 by 3 square. So intervals are of length 1 by 3 raised to k. Ck contains intervals of length 1 by 3 raised to k. And therefore, and we also know that there are 2 raised to k intervals. So the total length is, these intervals are disjoint. Therefore, the total length is 2 raised to k by 3 raised to k or 2 by 3 all raised to k. Now we are coming to the proof. So this is all about the Cantor set. How do we construct? And we can easily say that if you take a point in closed interval 0, 1, then there is a point close to this point which is not there in the Cantor set. The complement of Cantor set is kind of almost everywhere, has the property almost everywhere, since it kind of dense. So we are going to prove that in measurability, dense is something like in an epsilon neighborhood of a point, there exists a point which is not there in Cantor set, then complement of Cantor set is almost kind of dense. Now we are going to prove complement of Cantor set is kind of almost everywhere. Now that is measure of Cantor set is 0. So first we start with, so we need to prove Cantor set is closed, Cantor set is uncountable, Cantor set is of measure 0. First we prove that the Cantor set is of measures is measurable. So each step, C0 is a closed set, C1 contains union of closed sets, it's again closed intervals, it's again a closed set, C2 union of 4 disjoint closed intervals, again a closed set. So at any stage, Ck contains 2 raised to k closed intervals, and therefore the union of finitely many closed intervals is always closed. Therefore, Ck, C1, C2, C3, Ck's are all closed sets, and countable intersection of closed sets. Countable intersection of closed sets is again closed. Therefore, Cantor set is a closed set. If Cantor set is closed, then Cantor set is measurable, since every closed set is a Borel set, and we have proved earlier that Borel sets belongs to the sigma algebra of measurable sets. That is, every Borel set is measurable. Therefore, closed sets are measurable. Therefore, Cantor set is measurable. Now we prove that Cantor set is of measure 0. So if we take the length of intervals in Ck, center of measure of length of intervals, sum of length of intervals in Ck is nothing but 2 by 3 raised to k. We have seen this earlier. There are 2 raised to k intervals, and each subinterval is of length 1 by 3 raised to k. Therefore, total length is 2 by 3 raised to k. All these intervals are disjoint. Therefore, we can add up, and this you will get 2 by 3 raised to k. And this 2 by 3 is a value less than 1. Therefore, 2 by 3 raised to k decreases as k increases. And we have seen earlier that CK, this is a descending, we have seen earlier the continuity of Lebesgue measure in the case of descending collection, descending chain of measurable sets. So we have a descending chain here. We have C0, C1 is a subset of C0, C2 is a subset of C1, because we are taking C1, dividing this interval into 3 parts and removing one. We are not adding any points, we are just removing points. So the set is C1, C0, we remove some points, we get C1, we remove more points, we get C2. So this is a descending chain of measurable sets. Because all these sets are closed, all these sets are measurable. So we have a descending chain of measurable sets. Also, we know that C0 is of measure 1, closed interval 0, 1 is of measure 1. So by monotonicity, C1 will have a measure less than 1. All the measurable sets in the chain will have measure less than 1. Or we can easily say measure less than infinity, or all the sets are of finite measure. So this is important for the continuity of Lebesgue measure for a descending chain of measurable sets. So by continuity, we can say that measure of C is nothing but measure of the intersection of CKs and countable intersection of CK. The measure of countable intersection of CK is, since CKs are descending chain of measurable sets and C1 is of finite measure, this is nothing but limit n tends to infinity measure of limit k tends to infinity measure of CK. And measure of CK is 2 by 3 raised to k. 2 by 3 raised to k will tend to 0 as k tends to infinity. Therefore, Cantor set is of measure 0. Now we come into the last part. We prove that the Cantor set is an uncountable set. Suppose Cantor set is countable. Then we can assign a natural number to each element of the Cantor set. We can call them x1, x2, x3, etc. So every element, if Cantor set is not uncountable, that is, if Cantor set is countable, then we can assign a natural number to every point in the Cantor set. So we are not giving any order, but we are just giving them numbers. We pick some random number and random element and give it a number 1. Then we pick another point, we give it a number 2. So since the set is countable set, we can assign a natural number to every set, because the set of natural numbers is also countable. They are of same cardinality, therefore there always exists a natural number for each point in the Cantor set. And we have some point x1. We don't know which point it is. So this point x1 belongs to Cantor set means this belongs to C1, it belongs to C2, it belongs to C3, it belongs to all the sets in this descending chain. So if x1 belongs to C1, we know that C1 has 2 closed intervals. If we call them there are 2 closed intervals. We know closed interval 0, 1 by 3 and closed intervals 2 by 3, 1. So x1 belongs to C1 means x1 belongs to one of these intervals, because these intervals are disjoint. X1 belongs to one of these intervals, and we take the other interval. We call it F1. Closed there. So therefore C1 will have a point, a closed set which is not containing x1, because there are always 2 intervals. And again we take another point x2. We know there is another point x2 from C, and x2 belongs to C means x2 belongs to C2. x2 belongs to C1, x2 also belongs to C2. If x2 belongs to C2, then x2 belongs to, we can take something like C1. We already considered F1, right? So in C2 there are 2 intervals which are already there in F1. We divide F1 into 3 parts and remove the middle. Then we get 2 intervals in C2. 2 intervals in C2 which are contained in F1. At most, one of these intervals can contain x2. Not both the intervals cannot have x2, because these intervals are disjoint. x2 should belong to, at most, it can belong to one of these intervals. It cannot belong to both. So there is a set which is not containing x2. We call this closed set F2. We take x3. x3 belongs to C means x3 belongs to C3. Okay. x3 belongs to C3 means C3 has 2 intervals which are contained in F2. Again, by the construction, F2 has 2 intervals. We divide F3 into 3 and remove the middle portion, so we get 2 intervals. So F3 has 2 intervals in C3. F2 has 2 intervals in C3. Both intervals are disjoint. These intervals are disjoint, therefore X3 cannot belong to both. X3 will belong to at most one interval. We are not saying that X3 belongs to one of them. At most, X3 can belong to one of them. Therefore, the other interval will not contain X3, and we call this F3. Continuing like this, we will get a chain of closed sets, F1, F2, F3, etc. F1 is subset of C1, F2 subset of C2, F3 subset of C3. Also, we know that F1 contains F2, F2 contains F3. So this is a descending chain of measurable sets because F1, F2, F3 are closed intervals. These intervals are Borel sets and therefore measurable. Therefore, F1, F2, F3 are all measurable sets. So we have a descending chain of measurable sets again. But here we are not going to apply the continuity of Lebesgue measure. Here we are going to apply nested set theorem. So we know that these closed intervals are descending chain of closed intervals, and these intervals are all bounded. Therefore, by nested set theorem, the intersection of countably many closed bounded intervals, descending chain of closed bounded intervals is non-empty. There exists at least one point in the intersection of all these intervals. Therefore, there exists an X in this intersection. X belongs to k equal to 1 to infinity fk. Then X belongs to f1, f2, f3, etc. All these X belongs to all these intervals. And then we can see that X is not equal to ck for any k. If X is equal to ck, then X should not belong to fk, but we know that X belongs to fk. Therefore, X is not equal to ck for any k. Therefore, we have a point X which is not there in C. We have a point in C which is not there in C because we have counted all this. We have given number to all the elements. So every element in C can be numbered if C is countable. And then X is not there in C. This is a contradiction. Therefore, the set C is not countable. So this is a countable, this is an uncountable set. If we assume C is countable, then every element can be given a number. And then by the construction of C, we can obtain this descending chain of closed sets F1, F2, F3, etc. These are descending chain of bounded closed intervals, and their intersection is non-empty by nested set theorem. Therefore, there exists a point in these sets. There exists a point in the intersection, and we call this point X. And then X is an element of C, but it is not having a number. It is not of the form C. X C is not of the form CK. Okay, it cannot be given a number. It's not there in that family. Therefore, C is uncountable. Thus, we have an uncountable set of measure zero. Now we are coming to Cantor. In the next video, we will show that Cantor-Lebesgue function. We can construct Cantor-Lebesgue function from Cantor set, and we use this function to show that there exist non-Borel measurable sets. Thank you.